For number 1 for the review sheet, I have y is equal to 2 to the x power plus 4. The parent function is y is equal to 2 to the x power for this. And the only extra thing that I see is this plus 4. So I only have one transformation from the parent function, and that's that I'm going to be moving up 4. So that plus 4 at the end means I'm moving up 4. And if I'm moving up or down, it's going to affect my y values. And in this case, it's going to affect my y values by, I'm going to add 4 to all y's. So I'm starting with my parent function, which is y is equal to just the base that I have to just the x power. And for that table, I'm going to zoom in actually. I have -1, 0, and 1. And when I plug in -1, I get 0.5. And when I plug in 0, I get 1. And when I plug in 1, I get 2. And then all I'm doing is adding 4 to my y values. And when I do that, I'm going to end up with the table for y is equal to 2 to the x power plus 4, which the first point is going to become -1 and 4.5. The second point is going to be 0 and 5. And the third point is going to be 1 and 6. And before I plot those, I'm going to decide what's my horizontal asymptote. I know the horizontal asymptote is, I have a vertical shift of 4. So instead of being at y is equal to 0, where it automatically is, or it is for the parent function, I'm moving up 1, 2, 3, 4. I'm going to be at y is equal to 4 for that horizontal asymptote. And then I'll plot my points and make sure I don't touch that line. So I have -1 and 4.5. I have 0 and 5. And I have 1 and 6. And then I connect these, making sure I don't touch that horizontal asymptote. And that's my graph. For number 2, I have y is equal to -2 times 3 to the x power plus 1. The parent function here is y is equal to 3 to the x power. The extra stuff that I see plus 1 on the outside. That means I'm moving up 1. So all points are moving up 1, which means that affects my y values. I'll be adding 1 to all y's. And then the other extra thing that I see is this -2 in front. And that -2 means that I'm going to multiply all y's by -2. So that's a vertical stretch, and what actually happens to my points is I multiply them by that coefficient, the y values by that coefficient. I have my parent function is y is equal to 3 to the x power. And the table for that is -1 and 0.3, 0 and 1, and 1 and 3. And then I have these two transformations, the multiply the y's by -2 and add 1 to all y's as well. I have to do the multiplication first, so I'm going to multiply by -2, all of these points first. And then the next thing I'm going to do is I'm going to add 1. And I will end up with the table for y is equal to -2 times 3 to the x power plus 1. My first point is going to be -1 and 0.3 times -2 plus 1 is 0.4. And then I have 0 and -1. And then I have 1 and -5. And before I plot those points, I'm going to decide what's my horizontal asymptote. I have a vertical shift here. I'm moving everything up 1. So from where it was for the parent function at y is equal to 0, my new horizontal asymptote is going to be at y is equal to 1. And then I'm going to plot these points. So I have -1 and 0.4. And I have 0 and -1. And I have 1 and -5. 1, 2, 3, 4, 5. And then I'm going to connect these, making sure that I don't touch that horizontal asymptote. And this is my exponential function graph. All right, for number 3, I have y is equal to, y is equal to 3 times 2 to the x plus 1 power minus 2. I have 3 transformations here. One transformation that I have is this plus 1 in the exponent. And that means that I'm moving to the left 1. So, left 1. And that means I'm going to be subtracting 1 from all x's. Sorry. It affects my x's when it's in the exponent. Also, if I'm moving left 1, left and right affects my x's, not my y's. This minus 2 on the outside tells me I'm moving, all my points are shifting down 2. So everything is shifting down 2. And if I'm moving up and down, that's going to affect my y values. And this case is I'm going to subtract 2 from all y's. And then the coefficient here, I have, that tells me that that affects my y values. And it affects my y values by that I'm multiplying all y's by that number in front, which is 3 in this case. I'm starting with my parent function. So the parent function for this case is 2 to the x power. I know that I have -1 and 0.5. I have 0 and 1, and I have 1 and 2. And then I'm going to be subtracting 1 from all my x's, and I'll be doing 2 separate things to my y's. I need to make sure I'm doing the multiplication before the subtraction here. So I'm going to multiply by 3 first, and then subtract 2. And when I do all of this, I'm going to end up with the table for y is equal to 3 times 2 to the x plus 1 power minus 2. And my first point is going to be -2 and -0.5. And then my second point is going to be -1 and 1. And my third point is going to be 0 and 4. And before I plot these points, I'm going to decide what's my new horizontal asymptote, and it's at -2 since everything is shifting down 2. And that's my horizontal asymptote. And then I'm going to plot these points. So I have -2 and 0.5, or sorry, -0.5. I have -1 and 1, and I have 0 and 1, 2, 3, 4. And then I'm going to connect these, making sure I don't touch the horizontal asymptote. For number 4, I have the transformations that I see here are, I have this +3 in the exponent, and that means I'm moving from the parent function for this, I'm moving left 3. And if I move left 3, that's going to affect my x values. I'm going to subtract 3 from all my x values. From all x's, I have this coefficient here. Tells me that I'm going to multiply all of my y values by 4. And my parent function is y is equal to 0.5 to the x power. That's based to just the x power. I have the points for that are going to be -1 and 2, and 0 and 1, and 1 and 0.5. I left enough space in the x column so that I could do the transformations to it. So I'm going to subtract 3 from all my x values. For my y values, I'm going to multiply all of them by 4. So multiply by 4 for all of them. And I end up with the equation y is equal to 4 times 0.5 to the x plus 3 power, which is the function that I wanted after I do those transformations. And I'm going to end up with -4 and 8. 8 and -3 and 4, and -2 and 2. And before I plot those points, I'm going to determine where my horizontal asymptote is. It hasn't moved because there's no vertical shift. I'm adding nothing. So it's at y is equal to 0. Even if it's at y is equal to 0, make sure you still draw it. And then I'm going to plot these points and make sure I don't touch -4 and 1, 2, 8. -3 and 4, and -2 and 2. And I'm going to connect them, making sure I don't touch that horizontal asymptote. All right, number 5. Y is equal to e to the x minus 3 power. The parent function for this is y is equal to e to the x power. And I know the table for that is -1.4, 0, and 1, and 1, and 2.7. And then I'm going to, oh, whoops, I should have left enough space here because I can see that there's a transformation, which is why I do my transformations first. So I have -1, 0, 1. And I know that I have a transformation here of I'm moving to the right 3. So everything's moving right 3, which means that I'm affecting my x values, and that means I'm going to add 3 to all x's. So I'm going to add 3 to all my x's, and I'm going to end up with y is equal to e to the x minus 3 power, the table for that, after I take care of this transformation, which means I'm subtracting 3 in the exponent, and I'll have 3, wait, what? I'll have a negative, no, what? Oh my gosh, 2 and 0.4. I'll have 3 and 1, and I'll have 4 and 2.7. And I'm going to plot these points, but before I plot them, I'm going to just remember where my horizontal asymptote is. I have plus nothing, no vertical change, so it's at y is equal to 0. And I'm going to plot these points. So I have 2 and 0.4. I have 3 and 1, and I have 4 and 2.7. 2.7, and I'm going to connect them, making sure I'm approaching, but don't touch that horizontal asymptote. And then for number 6, I have y is equal to -e to the x power plus 3. This is the parent function for this is y is equal to e to the x power again. I know I don't have a horizontal change, so I don't have to leave space. I have -1 and 0.4, 0 and 1, and 1 and 2.7. I know one transformation that I see is this plus 3 here, and that tells me that I'm moving all of my points up 3. And if I move up 3, I'm adding 3 to all y's. The negative in front, this tells me that I'm going to be reflecting over the x-axis or multiplying all y's by -1. That's what's actually happening to the points from the parent function if you are doing a reflection over the x-axis. And then you end up with y is equal to e to, -e to the x power plus 3. And the table for that. And the table for that, you're going to have, oh, I'm sorry, I didn't do these transformations. You have to do the multiplying by -1 first. So multiply all of the y values by -1, because multiplication comes before addition or subtraction, and then you're going to add those 3 to each y value. And you're going to end up with -1 and 0.4 times 1 plus 3, 2.6, and then 0 and 2, and 1 and 0.3. And I'm going to, I know I have a vertical shift of 3, so I'm moving everything up 3, including the horizontal asymptote, so that's going to be at y is equal to 3. That's my horizontal asymptote, and then I plot these points to make sure I don't touch the horizontal asymptote. So I have -1 and 2.6, I have 0 and 2, and I have 1 and 0.3. And I'm going to connect them, making sure that I'm approaching, but don't touch that horizontal asymptote. And that's my graph. For number 7, I'm going to find the exponential functions that pass through the following points. So I have, for the first one, 1 and 10, and 5 and 160. This is one point. This is the other point. I'm going to make equations. So I have, when I am given 2 points or 2 ordered pairs with x and y values, I'm going to create a system of equations to solve. So for the purple, I want to put on top, or the equation I want to do first, because I want it to be on top, is the one with the bigger x value. So the bigger x value in this case is 5 instead of 1. So I'm going to use this x and y value, plug those into the formula y is equal to a times b to the x power. This is the general form for an exponential function, and after I get my two equations, I'm going to do something with them so I can solve for one of the variables and then solve for the other. I have, for the second point, I have, if I plug it into here, 160 is equal to a times b to the x power. For the blue point, I have 10 is equal to a times b to the, oh, why did I put x power? Oops, this should be the fifth power. I know what x is, it's 5 for that point. And then for the blue point, I have 10 is equal to a times b to the first power. What I'm going to do with these two equations, I'm going to divide the top one by the bottom one so I can cancel out the a's and I'm left with just one variable. I can solve a one variable equation. I can't solve a two variable equation. So I have to get rid of one of my variables. And in this case, because we have exponential functions and multiplication happening, dividing is what we're going to do to get rid of one of them. For the right-hand side, I have b to the fifth power divided by b to the first power. That's b to the 5 minus 1 power, or b to the fourth power. I have that is equal to 160 divided by 10 on the left-hand side is 16. I'm going to take the square root of both sides. No, I'm sorry, the fourth root of both sides, since I want to undo raising b to the fourth power. I'm going to end up with b is equal to the fourth power of 16 is plus or minus 2, but it's just positives for these exponential functions. B has to be positive. So b is equal to 2 here. And then I have, I'm going to plug that in. So this is my growth rate. I'm going to plug that growth rate into one of the equations that I have to solve for what a is. So I'm going to use the one with the smaller numbers, the second one. 10 is equal to a times b to the first power. And I'm going to plug in that b is 2. So I'm going to plug in 2. 2 to the first power is just 2. I'm going to divide both sides by 2. I'm going to divide both sides by 2. And that's going to give me that a is equal to 5. So I have a is equal to 5. And b is equal to 2. My equation is y is equal to 5 times 2 to the x power. This is my initial value. This is my growth rate. All right, for the second one, I have 2, 8 and 3, 32. I'm going to color code them. This one blue, this one purple. I'm going to take the one with the bigger x value. That's this one. This point, it has a bigger x value. And I'm going to write the equation using this x and y. And I will have 32 is equal to a times b to the third power. And then for the second point, I use this x and y value. I'll have 8 is equal to a times b to the second power. I'm going to divide these two equations to get rid of my a's. And I'll be left with b to the 3 minus 2 power, or b to the first power. I just have to write b is equal to 32 divided by 8, which is 4. So I know my b is 4. That's my growth rate. I'm going to plug that in and see what I get for a. Into one of my equations, I'm going to use the one with the smaller numbers. So 8 is equal to a times b to the second power. I'm going to plug in b is 4. And that's going to give me 16 times a, gives me 8. I'm going to divide both sides by 16. And I'm going to get that a is equal to 1/2. And so I'm going to plug these two things into my general form. So I'll have y is equal to 1/2 times 4 to the x power. This is my initial amount, and this is my growth rate. And that's my function. For the next one, I have -1 and 1 over 15 and 2 and 25 over 3. I'm going to take the one with the bigger x value, and I'm going to write that equation first for my system of equations that I need to write to solve. So the one with the bigger x value is the purple point again. I'm gonna, this is my x value, this is my y value. I'm plugging it into the general form. Y is equal to a times b to the x power. I have 25 over 3 is equal to a times b to the second power. And then for the first point, I take this x and y value and I plug them into this general form. And I get 1 over 15 is equal to a times b to the negative first power. I'm going to divide these two equations. And here's something that you can do if you don't like to deal with the fractions. So if you don't want to deal with the fractions, you could convert them into decimals. So if you prefer, I'm going to do alongside this, you could do 8.3 repeating is equal to, is equal to a times b to the second power. And then the second equation 1 divided by 15 gives me, in decimal form, I have 0.06 repeating. So 666, or 667 is equal to a times b to the negative first power. I'm going to divide the two equations to cancel out my a's. I'll do that for both of these. I'm going to end up with, on the left, if I do this, I'll have 25 over 3 divided by 1 over 15 on the left-hand side is equal to b to the 2 minus negative 1 power. So that's 2 plus 1, so that's b cubed. I have b cubed is equal to 25 over 3 divided by 1 over 15. When I have dividing by a fraction, I change the division to multiplication, and I change the second fraction to the reciprocal. So I have 15 over 1. And I'm multiplying that to 25 over 3 now. And that gives me b cubed. I'm going to simplify what I can. 3 goes into 15 5 times, so I change this to 1 and 5. And I'll get 25 times 5, which is 125, is equal to b cubed. I'll take the cubed root of both sides, and that will tell me that b is equal to 5. If I do it the other way, so if I do this, I'm going to get b, I'm not going to get the exact right answer. So b squared divided by b to the negative first power is b cubed. So you should be doing it with the fractions, actually. But let's see. 8.3333. Repeating, divided by, divided by 0.066. Yeah. It has 124.99 and 325. So, you round that to 125. And then you take the cubed root of both sides. Actually, just don't do it this way. I'm sorry. Don't do it this way. Do it with the fractions, because otherwise you're not going to get the right answer, because they're repeating decimals. Okay. All right, so I end up with b is equal to 5. That's my growth rate. And then I plug that into one of my formulas. So I'm going to plug it into 1 over 15 is equal to a times b to the negative first power. Actually, just kidding. I want to plug it into the other one because I don't like negatives. So I have negative exponents. So I have 25 is equal to a times b to the second power. I'm going to plug in that b is 5. So I have b is 5. I'm going to have 25a is equal to 25 over 3. I'm going to divide both sides by 25, I'm sorry. And actually, what I want to really do, because I have a fraction on the other side, I'm going to multiply by 1 over 25, which is the same as dividing by 25. And I'm going to end up with a is equal to, these 25s cancel out, and I get 1/3. So a is 1/3, b is 5. I'm plugging those into my general form. So I have my general form is y is equal to 1/3 times 5 to the x power. And this is my, this is my initial amount, this is my growth rate, and this is my function. That fits both of these points. All right, number 8. Identify the following as growth and decay. What I'm looking for is the value of the absolute value of b greater than 1. That means it's growth. If it's less than 1, it is decay, but only if a is positive. only if A is positive. All right, so I have the first one, the base is E, so I know that, or the growth rate is E, so I know that that's 2.7 and change, which means this is growth. For the second one, the growth rate here is 0.5, and I have a positive coefficient, just like I did in the first one. Sorry, I didn't say. And that is less than 1, so this is decay, since it's a fraction. For the third one, I have a positive coefficient and a base that is greater than 1, so this is growth. And then for the last one, I have 1/2, which tells me that this is decay, since B is less than 1. But then this negative in front flips it upside down. So instead of looking like this, it's going to flip upside down and look like this. So it's actually going to be growth. And you can plug in points and see plug in points for X and see what you get for Y. Just 2 points you would need to do that to see if it's decreasing as you read left to right, or as your X increases, or is it increasing as your X increases. So decreasing or increasing as your X increases for your Y. All right, for number 9, this is a word problem. For these word problems, first thing I want you to do is decide between those three functions that we talked about for exponential growth. The first one is y is equal to a times b to the x power. That's the general form for exponential function. The other two are compound interest formulas. Compound interest formula 1 was a is equal to p times 1 plus r over n to the nt power. That's for when it's compounded a specific number of times per year. And then the other one was a is equal to p times e to the rt power. These two, you're only going to use if the word problem says compounded. If the word problem doesn't say compounded, you use this one. If the word problem says depreciates, you have to use this one because you're only appreciating for compound interest. Compound interest is putting money into a bank account and the bank giving you money on that, giving you interest on that money. So you're always going to have a bigger balance at the end than you did in the beginning, than you invested. This is for a specific number of times compounded per year, and this one is for continuously compounding per year. All right, for the first problem, you invest $2,300 into a bank account that compounds continuously. I don't have to continue looking at the rest of this. I know compounds continuously tells me I'm using the compound interest formula for compounds continuously. That second one, a is equal to p times e to the rt power, because I see the word compounds and I see the word continuously. All right, so now I want to see what was given to me. I have to be careful with the cash amount that's given to me if it's my A or my P. P is what you invest. It's your initial amount. A is the final amount. You invest $2,300 tells me this is my principal. This is my investment. So P is equal to $2,300. I see this annual interest rate per year. That's what annual means. That interest rate per year tells me the rate is the decimal form of that 0.03, and then T is 7 years have passed by. I'm plugging in those numbers into the formula. I have A is equal to 2,300 times E to the 0.03 times 7 power. When I do 0.03 times 7, I get 0.21. So I have 2,300 times e to the 0.21 power. And when I do e to the 0.21 power in my calculator, I get a number that has a lot of decimals. And then I multiply that by 2,300. And I get $2,837. And I round to the nearest hundredths place, since we have pennies. And I get 46 cents. Yeah, 46 cents. And that's my answer of how much money I'll have after 7 years. And notice it is more than the original, which it should be. For number 10, your grandmother set up a bank account for you as a very generous present 12 years ago. The bank compounded continuously. Oh, compounded continuously means I'm using this formula. So I have A is equal to P times E to the RT power. Now I want to see what information was given to me. So I know the time is 12 years because this was 12 years ago. the bank compounded continuously at 4.2%. So I know the rate is 0.042. You just check the balance and there is this much money. You just check the balance. This is what is there after the 12 years have already passed by. So this is at the end, which means it's our P. Be careful. Sorry, not our P, our A. This is A. A is equal to $28,252. Because that's the end amount in the account. And I want to know how much did your grandma originally invest for you. So I want to know what P is. I don't know what P is. I have to solve for it. I'm plugging in A is 28,252. I don't know what P is. I'm leaving it blank. Or I'm just leaving it P to represent the principal or the original investment. I have e to the 0.042 power, 42 times 12 power, and that's actually the 0.504 power, so I have e to the 0.504 power times p gives me $28,252. E to that power, so e to the power of 0.504 is 1, so I have p times 1.655 363, and you want to write as many decimals as your calculator gives you. And then you're gonna, if you have a calculator that lets you divide by the answer, you can do that instead. But you're gonna divide by 1.655 363. So I have 28,252 divided by, this number gives me 17,067.30 when I round to the nearest hundredths place, which I always do for money. All right, number 11, I have fish in a pond are increasing at an annual rate of 18%. The initial population was 343 fish. How many fish will there be in 3 years? Okay, there is no compounded here, no word compounded, so I'm using y is equal to a times b to the x power. I need to find my initial amount. I need to find my growth rate. In this case, I have my initial amount. So the initial amount that I'm starting with, or my A value, is the initial population was 343 fish, so it's 343. I know B, or my growth rate, is 18%, and it's increasing, which is important. I need to know if it's increasing or decreasing. I need to calculate what B is. I'm converting this percent to decimal form, and adding it or subtracting it from 1. Since it's increasing, I'm adding it. So 1 plus this gives me 1.18, and that is my growth rate. I'm plugging these in into the formula. So I have y is equal to 343 times 1.18 to the x power. And in the x power is how many time periods have passed by. And since it doesn't specify, it said annual rate, so that's every year. Since it's every 1 year, 3 years, that's 3 time periods, so I put 3 as the exponent. I have 1.18 to the third power times 343 gives me 563 fish and change, but I round down, even though I'm technically supposed to be rounding up. I round down because this is a living thing and I'm talking about increasing. So that with the population, since it was increasing, it's going to be 563.55 blah blah blah, but I can't have a piece of a living thing, so it's 563. I round down. For number 12, fishing in a neighborhood pond fish in a neighborhood pond have caught a terrible fish disease. It's killing them. If the fish are decreasing, dying at an annual rate of 23%, and there are 800 fish right now, how many will there be in 30 months? For this problem, I know that I see the word decreasing and I don't see the word compounding. So I know I'm using y is equal to a times b to the, actually, let me write this over here. Y is equal to a times b to the x power. If it's decreasing, it can't be compound interest. So decreasing means it can't be compound interest. My initial amount here, so the initial amount is, there are 800 fish right now, so 800. And the growth rate, or the B, is going to be 23%, but decreasing. So decreasing means I'm taking 0.23 and I'm subtracting it from 1. And that's going to give me, when I do that subtraction, 0.77 is my growth rate. And so I plug these numbers in to my formula. So I have 800 times 0.77 to the x power. So 0.77 to the x power. And in this case, x is, I know I'm talking about 30 months. This is the annual rate, so I need to convert 30 months to years. So the time that has passed by is, I take 30 months and I multiply by 1 year per 12 months. When I do that, I cancel out months, the unit months, and I'm left with 30 times 1 year gives me 30 years, or 30 over 12 years, and that is 2.5, so the time is 2.5 years. So I'm putting 2.5 here, and I'm going to have 0.77 to the 2.5 power, and then I'm going to multiply that by 800, and I get 416.21. I round up to 417 fish because I'm decreasing here, so I'm actually losing fish. I can't lose a piece of a fish, so instead of rounding down in this case, I'm rounding up. For 13, carbon has a half-life of 5,730 years. How much C14 would be left for a 22 milligram sample after 2001 years? This is a half-life problem. I don't see the word compounded. Y is equal to a times b to the x power. And I'm going to make sure I take into account that the growth rate is being applied every 5,730 years. Every 5,730 years, the growth rate is being applied. I know that my initial amount here, so the initial amount is 22 milligrams, so 22. I know the growth rate in this case is half-life. It tells me what the growth rate is. This doesn't give me a percent. I don't have to calculate it. I know it's 1/2. It's dividing by 2 or cutting in half or multiplying by 1/2 every 5,730 years. And then in this case, because it's not every 1 unit, it's every 5,730 units, I need to also take into account my time period, how long a time period is. And that's 5,730 units. So when I create my equation, I'm doing y is equal to that 22. So 22 is my initial amount times the growth rate, which is 1/2, to the x power. But this should be the number of time periods that have passed by. So I want to be able to plug in a number of years and get the number of time periods in my exponent. So I need to make sure I also divide by that time period. That means if 2,000 years have passed by, if I divide that by 5,730, I can see how many time periods that actually is. All right, so I'm going to plug in now that I have this. I'm going to plug in 2001 years because that's how many years have passed by. And I will get 2001, 1 divided by 5,730 gives me 0.349 and a bunch of other numbers. So I have 1/2 raised to the 0.3492146 power, and I raise 1/2 to that power, and I get a number, and then I multiply that number by 22, and I get 17 points, and I'll round to the nearest hundredths place, 0.27 milligrams. Okay. All right, and then number 14, I have the bunny population doubles every 2 years. If there are currently 89 bunnies, how many will there be in 200 years? First things first, this is y is equal to a times b to the x power. No compounded, no word compounded, and this is also, oh no, it's increasing. No word compounded. I want to find my initial amounts. So the initial amount in this case is 89, and I'm starting with 89 bunnies. The b is, it gives me what the growth rate is by saying doubles. That means b is 2. And then I know the time period is every 2 years. So, whoops. Stop. The time period, oops, is every 2 years this happens. So it's not every 1 year, it's every 2 years. So I need to make sure I'm taking into account that time period. So my formula is going to be y is equal to 89, the initial amount, times 2, whoops, raised to the x divided by 2 power. That means whatever amount of years have passed by, I'm going to divide that by 2, so I get the number of time periods that have passed by. And that's what your exponent should be, the number of time periods that have passed by. I have y is equal to 89 times 2 to the, in this case, I'm talking about 200 years passing by, so 200 divided by 2. That's y is equal to 89 times 2 to the 100th power. 2 to the, this is going to be a really big number. 2 to the 100th power times 89 is equal to 1.128 times 10 to the 32nd power bunnies. So you're going to have to write it in scientific notation because it's too big of a number to write. This actually doesn't make sense because the mass of this amount of bunnies would be more than the mass of the Earth. So that question doesn't make sense.